Okay, so this talk is about space lower bounds for graph processing algorithms. So why do we care about such lower bounds and such algorithms? Well, this is because graphs are a common abstraction for representing real-world data, and they're used for processing modern networks such as social networks, web topologies, interaction graphs, whatnot. And one common feature of modern graphs is that they tend to be very large. So very often we cannot really fit these graphs into the memory of our computers, so we're interested in designing graph analysis primitives that use very limited space. And this is the setting studied in the streaming model of computation. This is our model of computation for this talk. So for the purposes of this talk, our input is a graph G. There are n vertices and m edges. In the streaming model of computation, we think of the vertices of the graph G as known, maybe numbered 1 through n, and these are represented by the green dots on the slide. Now, the edges of the graph G are presented to the algorithm in a stream in an arbitrary order, like this. And really, think of reading the edge set of the graph off disk. So as the algorithm is reading the list of edge updates of the graph, it is limited in space usage, so it cannot just store the entire graph and solve the problem offline. Instead, the algorithm makes one or more passes over the stream and has to output the answer in the end. Of course, we're mostly interested in single-pass algorithms. We want to just look at the data once, use very limited space, and output the answer. Well, the problem of designing algorithms for graph problems in the streaming model of computation has received a lot of attention. We know how to solve many graph problems in this manner. For example, we know how to construct graph sparsifiers, or find large matchings in graphs, or approximate distances in graphs in this way, and many other questions. Well, a very common assumption that we make is that while edges of the graph do not fit into the memory of a single compute node, we usually assume that at least the vertices of the graph do. So this is the reason why in the graph streaming or semi-streaming model of computation, the standard assumption is that the algorithm can use n polylog n space. So n is the number of vertices in the graph. And this is very reasonable. For many problems that have been considered in the streaming model of computation, space linear in the number of vertices is definitely necessary. And sometimes this is for very clear reasons. It is often the case that just the sheer size of the object that we're computing is linear in the number of nodes. Think of computing a large matching in the graph or finding a sparsifier or spanner. Well, there are other settings in which the bound holds for less obvious reasons. For example, if we want to determine connectivity, we still need to use at least linear space, even though the size of the output is just one number. Well, it turns out, however, that this bound is not universal. In a SOTA paper last year, we gave an algorithm for approximating the size of maximum matching in a graph given as a stream of edges in a random order to a polylogarithmic factor while using only polylogarithmic space in the size of the graph. So this is interesting and gives a solution with space requirements exponentially smaller than previously known. In general, this is the best known algorithm, the first known algorithm for a graph problem that uses space sublinear in the number of vertices of the graph. And this suggests the following question. Well, can we find other graph problems for which we can approximate the cost of the solution, perhaps without computing the solution itself, while using space sublinear in the number of vertices? Well, for our matching size result, it was crucial to assume that the order of the edges was not worst case. We're assuming that the edges arrive in a random order in the stream, and in general, we're happy to make these assumptions. Now, if we want to be very ambitious, what we would like to shoot for is an algorithm for solving other graph problems or approximating solution cost using space polylogarithmic in the size of the graph. And again, if we want to make the assumption that the edges arrive uniformly at random, this is fine. Well, this is the problem that we consider in this work. And the problem that we look at is max cut. So the question is, suppose that we're given the edge set of the graph as a randomly ordered stream. Is it possible to get a good approximation to the value of max cut in this graph using space polylogarithmic in the size of the graph? Okay, so the talk is mostly about max cut. Let me remind you what max cut is and what we know about it. So in the max cut problem, we're given a graph, such as the graph shown in the picture, and our task is to find a cut in this graph that cuts as many edges as possible. Here's one such example of a cut, which is shown in red. It cuts all but 2 edges in the graph and is optimal. Well, what do we know about approximating max cut? For example, there's a trivial factor 2 approximation to max cut value. We know that a uniformly random cut in the graph cuts half the edges in expectation. So this is a trivial factor 2 approximation. We know how to do better using the Goemans-Williamson algorithm or using spectral techniques by Trevisan and their combinatorial implementations by Kali and Shashadri. Okay, so what does this imply for streaming algorithms for max cut? Well, the trivial factor 2 approximation achieved by simply looking at a random cut yields immediately a trivial algorithm that gives a factor 2 approximation in polylog space. For that, all we need to do is just count the number of edges in the graph and output that number divided by 2. At the other extreme, we know that if we're willing to spend space linear in the number of vertices in the graph, then we can have an arbitrarily good 1 plus epsilon approximation, at least information theoretically. So this is achieved by simply storing a random sample of n over epsilon squared edges of the graph. So the question that we ask in this work is, well, is it possible to do better than the trivial factor 2 approximation while still using polylogarithmic space and the size of the graph?
This mapping is not entirely obvious if you don't know ahead of time how many edges there would be, right? I mean, how do you know what n over epsilon squared is?
Right, so I guess you can, you can get, yeah, this assumes that you know the number of edges, but you can always guess to
also assume they were in a random order, right? So
no, this wouldn't even need the assumption that it's in the random order. You just sample the edges. That's a good question. Okay, so the question that we want to ask is, well, is there something more interesting at this extreme of the spectrum? So can we do better than factor 2 while still using polylogarithmic space? Okay, and our main result is that, well, unfortunately, this is not possible. We show that any single pass streaming algorithm that approximates the value of max cut to a factor slightly better than 2 minus epsilon for any constant epsilon, necessarily uses space polynomial in the size of the graph. In particular, at least square root n space is required. Now, furthermore, this bound holds even if the edges of the graph are presented to the algorithm in a uniformly random order. Well, so this result rules out the possibility of achieving non-trivial algorithms for approximating max cut value in polylog space, but as we will see later, the techniques that we use suggest that sublinear space algorithms, in particular algorithms with roughly root n polylog n space, might be possible in some settings. So this is the main result. We also show that getting arbitrarily good 1 plus epsilon approximations to max cut value in adversarially ordered streams essentially requires linear space. This result was also independently and concurrently achieved by Kogan and Kraft-Gammer. Okay, so for the rest of the talk, I will focus on the main result, namely beating the trivial factor 2 approximation requires at least square root n space. Well, and we established the main result by using and analyzing the following hard distribution based on random order-Schreiber graphs. So there will be 2 cases, the yes case and the no case. In the yes case, the input graph will be a random bipartite multigraph. There will be very few repeated edges, with expected degree roughly 1 over epsilon squared. So recall that epsilon is our precision parameter. We're trying to prove impossibility of obtaining 2 minus epsilon approximations to max cut. Now, in the no case, our input will be a random non-bipartite, essentially a random non-bipartite Erdős-Rényi graph with the same average degree. Now, since in the yes case, the graph is bipartite, the max cut value is naturally all the edges of the graph. It's just m. In the no case, we will show that, or it's easy to see, that the max cut value is not much bigger than half of the edges of the graph. So the graph that we will see in the no case is very far from being bipartite. Okay, so since there is a gap between max cut value in the yes and no cases for our input distribution, it is sufficient to just concentrate on this distribution and show that square root n space at least is required to distinguish between the two in the streaming model.
So in the yes case, you pick two, both sets are equal size?
There will be, right, so there will be sampled, the size of each set will be, so each vertex will belong to one side of the bipartition with probability 1/2 and to the other side with probability 1/2. So there'll be slight deviations. Any other questions? Okay, so this is the hard input distribution. And so it's based on Erdős-Rényi graphs. So before I define the distribution properly, let me remind you some of the basic properties of Erdős-Rényi graphs that we will need. So recall that a graph G is sampled from the G and P distribution if each edge, each pair UV, is an edge in the graph G independently with probability P. And the graphs that we will be interested in will be Erdős-Rényi graphs below the connectivity threshold. So the value of P that we're interested in is alpha over n, where alpha is a sufficiently small constant. So it is known that if alpha is sufficiently small, then such graphs with overwhelming probability are unions of very small trees. The sizes of these trees are no bigger than log n.
There's also a Poisson number that are one edge more.
Again?
There's a Poisson number of those with one edge more.
Right. Yes, if alpha is small enough, they don't happen. So that's why it's not very high probability. So with probability 1 minus order alpha cubed, we won't see any of those. Okay. Good. And so now I can define the hard input distribution. So recall again that we're trying to prove that square root n space is required to get 2 minus epsilon approximation to max cut. So epsilon is our precision parameter. So the hard input distribution will be naturally partitioned into k phases, where k is about 1 over epsilon squared. So in each phase in the input stream, the algorithm will be presented with a independently sampled, random bipartite Erdős-Rényi graph below the connectivity threshold. So in the yes case, the input will look like this. There are k phases, and in each of the phases, an independent bipartite Erdős-Rényi graph arrives. All these graphs share the same bipartition. So in particular, if we put them together, the result is a bipartite graph. Now, the no case is very similar. Again, in each of the phases, a random bipartite Erdős-Rényi graph arrives, except that they do not share the bipartition. The bipartition is resampled uniformly at random in each of the phases. Because of that, we can see that the max cut value is exactly all the edges in the yes case, and is not much bigger than half of the number of edges in the no case.
And the streams arrive in random order, so there's a permutation applied to the entire...
That's a good question. So we will analyze the process as is, and then show that the ordering in which the edges arrive is within little o of 1 in total variation distance from uniformly random ordering. So if you look at the graph that is finally generated, the order in which the edges arrive here is uniformly random. So basically think of each of the subgraphs as arriving in a random order. Okay, so this is our distribution on inputs, and now we will need to analyze it. We will use the following natural k-party communication problem for that. So there are k-parties corresponding to the phases of the input, so roughly 1 over epsilon squared players. Each player, so the jth player, receives the jth phase graph as input, as well as a message from the previous player, and given this information, constructs his own message and sends it to the next player. Now, and finally, the kth player has to announce the answer. Was it the yes case or the no case? Now, the connection to streaming algorithms is, of course, that any single-pass streaming algorithm for distinguishing between these yes and no cases immediately leads to a protocol for this k-party communication problem. The first player simply runs the streaming algorithm on their input, then ships the state of the memory to the next player, and they proceed in this fashion. So let me define a sequence of random variables, or rather 2 sequences of random variables that represent the state of the streaming algorithm after reading the jth phase of the input. So sj yes will be the random variable that corresponds to the state of the algorithm after reading the jth phase in the yes case, and sj no is the same random variable for the no case. So what we know is that if we start with a streaming algorithm that approximates max cut to better than 2 minus epsilon factor, then the following is true. Well, the first elements of these two sequences are the same because the algorithm starts in the same state in the yes and the no cases. And on the other hand, these two sequences diverge in total variation distance after k steps. What we want to show is that if this is the case, then the streaming algorithm must use a lot of space, at least square root n. Now, if we were to analyze this k-party communication problem, it is not immediately clear how to do this. So first one would have to reason about arbitrary ways of compressing graphs, which we would like to avoid. And second, this is a k-party communication problem we would like to work with simpler two-party communication setting. So instead of looking at the problem directly, what we do is define a two-party communication problem and reduce it to approximating max cut on this distribution. The benefit of this is that now we only have to reason about compressing information about this hidden by partition, as opposed to the graphs that we see in the stream. And this will be easier. So let me define the problem. Now, the two-party communication problem that we use is something that we call the Boolean hidden partition problem. And this is a variant of the Boolean hidden matching problem defined by Gavinsky, Kempe, Kyrianidis, Raz, and DeWolf. So in this problem, there are two parties, Alice and Bob. Now, Alice gets a binary vector x of length n as input, and it's good to think of this vector as encoding a bipartition of the vertex set of our graph. So the vertices of the graph are shown here as the green dots, and each vertex is labeled by 0 or 1. 0 means it goes on one side of the bipartition, 1 on the other side. Now, Alice receives the string x, then compresses the string into a message m, and sends the message to Bob. Now Bob, together with the message, gets the following two pieces of input. So first, Bob gets a graph G on the vertex set n, as shown on the slide. Now, each edge of the graph G is further annotated with a label W. So here are the labels shown as zeros and ones. The labels convey the following information. In the yes case, the label on each edge, UV, is nothing but the sum, modulo 2, of the two bits corresponding to the endpoints, xu plus xv. So hence, in the yes case, the labels convey for each edge the information of whether or not the edge crosses the bipartition held by Alice. Now, in the no case, however, right, so for example here, you see that those edges that have zeros do not cross the bipartition, and they're shown as orange. Now, in the no case, however, the labels are uniformly random and have exactly nothing to do with the bipartition that Alice holds. The following operation will be used later. So note that if Bob is getting a graph G as input together with labels W on the edges, what Bob can do is look at each edge in the graph and only keep those edges that have ones written on them. In the yes case, this will have the effect of only keeping those edges of the graph that cross the bipartition held by Alice. In the no case, this will amount to just subsampling the graph uniformly at random. Okay, so this is a problem. This problem is an extension of the Boolean hidden matching problem defined by Gavinsky, Kempe, Kyrianidis, Raz, and DeWolf, and then further studied by Verben and Yi. Now, the difference is that for their problem, the graph G that Bob was receiving was a uniformly random matching on a constant fraction of the nodes, and it is important for us that the graph should be a uniformly a random Erdős-Rényi graph because we're dealing with a uniformly random edge arrivals. So this is the Boolean hidden matching problem. Now, in fact, we will use a natural distributional version of this problem. So something that we call D-BHP. In this distributional version of the problem, Alice gets a uniformly random string x. So think of a uniformly random bipartition of the vertices of the graph. And Bob gets a graph sampled from the GNP distribution. This is a graph below the connectivity threshold of GNP. Now, we are in the yes case, independently with probability 1/2, and in the no case otherwise.
What lower bound on M are you going to prove? On the length of the messages?
Square root n. Square root n.
I'm just kind of confused. So why can't Alice just send a bunch of vertices that are on the same side, and then Bob will see?
The question is how many. So, for example, she can send square root n vertices, right?
That sends a constant number. Won't she see?
If she if she sends a constant number of vertices, then see Bob's graph is a Erdős-Renyi graph below the connectivity threshold. So think of really very small components. You need to get, let's say, at least one edge in that set. So square root n vertices is exactly the threshold at which this will work, and this is the bound. That's a great question.
So what's the meaning of the last? What do you mean by S case independently?
We defined a distribution on inputs. So inputs are defined, we first flip a coin, and with probability 1/2 is the yes case, with probability 1/2 is the no case. That's the distribution on inputs. And the task is to distinguish between the two cases. Any other questions? Good. Okay, so we show a reduction from the distributional version of the Boolean hidden partition problem to approximating max cut value. So specifically, we show that any single pass streaming algorithm that approximates max cut value to a factor better than 2, to 2 minus epsilon, say with probability 99%, yields a protocol for the distributional version for Alice and Bob that allows them to achieve advantage at least omega epsilon squared, epsilon is our precision parameter, over random guessing, for whether or not it was the yes or the no case. Now later we will prove that, that any such protocol has to have communication at least square root n, and this will give the result. Okay, so this is the task. So let's see how this works. We're given an algorithm for approximating max cut value to a factor better than 2, and we want to design a protocol for our two-party communication problem. Now, of course, the main issue is that the distribution on our inputs naturally consists of k phases, and we want a protocol for a two-party problem. Now, it turns out, however, that we can do this, and this is essentially by the hybrid argument. So again, recall that we defined this set of two sequences of variables, S0, S1, S2 in the yes case, and the same set of sequence of variables for the no case. We know, so these variables represent the state of the streaming algorithm as after having read the jth phase of the input sequence. So we know that initially, these two sequences start out at the same, being equal, because the algorithm starts in the same state, and they diverge in total variation distance over the k steps of the process. Now, in particular, what this means is that there must be at least one step j star, to recall the informative index, where this divergence was non-trivial. So the total variation distance between the distribution of the state of the algorithm and the yes case at step j plus 1 should be at least omega 1 over k bigger than the total variation distance at the previous step. And this is exactly the index that we use. So given her input x, which encodes the bipartition of the graph, Alice will run the streaming algorithm up to this informative index, and then ship the content of the memory of the algorithm to Bob. Now, given that, Bob will generate, so recall that Bob has a graph G with labels on the edges. Now, given this graph G, Bob will simply keep those edges that have 1s written on them. In the yes case, this will nicely generate the next stage of the input process. In the no case, this will give a uniformly random subsampling of his graph. One can see that from the distribution of the state of the algorithm at step j star plus 1, one can distinguish between the yes and the no cases with advantage at least 1 over k. Okay. So this is a reduction from approximating max cut value to our problem. Now it remains to show that solving the distributional Boolean hidden partition problem requires communication at least root n in the two-party setting. And I won't get into the proof, but let me just say that the proof uses Fourier analytic techniques. It follows the steps of Gavinsky, Kempe, Kernidis, Raz, and de Wolf, And the difference that we have to handle is that in their case, the graph that Bob was receiving was a uniformly random matching of a fixed size. In our case, this is a random Erdős-Rényi graph, but this can be handled. Now, let me skip the details of this. Okay, so what we just saw is the following. I first defined a distribution over inputs, where any algorithm, any streaming single-pass algorithm that approximates max cut value to a factor better than 2 requires at least square root n space. Now, the graph was just, so the result as advertised was a result for a uniformly random ordering of edges. One can show, however, that the ordering of edges in the stream that we defined is close in total variation distance to a uniformly random ordering. And this gives the final result. Okay. So this was a space lower bound for the setting where the graph arrives in a uniformly random order. In fact, a similar impossibility result can be proven for a related setting, where the stream contains not the edges of the graph in a uniformly random order, but rather n polylog n I.I.D. samples of the edges of the input graph. One can also see that this bound is tight for our distribution, because essentially what we're showing is that it is hard to distinguish between a random, reasonably sparse Erdős-Rényi bipartite graph and a non-bipartite graph without using square root n nodes, a square root n space. One can see that this bound is tight for this distribution because one can sample uniformly at random roughly square root n vertices in the graph and maintain random walks of logarithmic length out of these vertices. Now, in the case that the graph is bipartite, we'll maintain the walks of even and odd length. If the graph is bipartite, that is, where in the yes case, the even and odd random walks will not intersect. In the case when the graph is non-bipartite, the walks will mix in log n steps, and by the birthday paradox, we will see some intersections and we will be able to distinguish between the two cases. Okay. So what this shows is that the bound is tight only for our particular distribution. But a very interesting open problem would be to see if a better than factor of 2 approximation for max cut value using similar techniques, so let's say polylog n length random walks in the streaming model using roughly root n space, could be obtained for the general problem. And of course, the very interesting problem is to obtain other streaming algorithms for other graph problems where in space sublinear in the number of vertices of the graph. Thank you.
Questions?
Do you can list some other parameters that are can separate these two distributions? Clearly, max cut is not only parameter that is very different for these two distributions.
Oh, I see. That's a good question. Right. So essentially, the way it's a good question. I don't know. So this seems to be saying something about the hardness of doing long-range exploration in the streaming model without using small space, right? So the only way of distinguishing between the two cases is basically by doing long random walks, and this seems to be saying something about this. But I'm not sure if I have better formulations or more general properties that distinguish.
It seems that the same approach might give a space lower bound for online distinction between a forest and a graph with at least one cycle. Because graphs you're choosing are so thin.
Oh, I see.
Yeah, they're so sparse that they don't have cycles.
Right. I see. So you're saying that distinguishing between the case when, let's say, these log n size trees never had a unicyclic component and actually did have a unicyclic component. Right. That seems interesting.
Following up on this, girth and odd girth might be, again, parameters that these technologies could apply to.
Can you,
You're looking for graphing the odd girth.
oh, so what is the odd girth? This is
Shortest odd cycle.
shortest odd cycle. Yes, I see. So this, I guess that's a lower bound for that, right? Right. Sure.
Okay, thank you.